Look at this glowing crescent. I mean, for most of human history, it was just this beautiful, mysterious light hanging up there in the night sky. But what if I told you that you absolutely don't need to be an astronaut or have $1 billion spacecraft to uncover its deepest secrets? Today, I want you to step into the shoes of an observational astronomer with me, because by simply analyzing the interplay of light and dark on this distant sphere, we're going to completely decode the moon's violently beautiful geological history. Welcome to this explainer. Reading the Moon, Shadows, Seas, and Stone. In this explainer, we are diving into a really fascinating premise, the idea that we can understand massive planetary-scale formations, things like craters, ancient lava seas, and totally rugged mountain terrains, using literally nothing but the visual evidence of light and shadow. We're not just looking at pretty pictures today, we are reading a geological text. And I promise you, once you learn this alphabet of shadows, seas, and stone, the moon is never going to look the same to you again. It's practically screaming its history at us if we just know how to look. Okay, let's dive into this. Section 1. The Power of Shadows Illuminating Topography. Now, to actually read the moon's surface, we have to start with a concept that feels, well, a little counterintuitive. We usually assume that to see things clearly, we need as much light as possible, right? But on the moon, to truly see the landscape, we actually need the darkness. And this brings us to a really crucial astronomical concept, the Terminator line. This is the exact dividing line between the moon's day and night. Think about what happens here on Earth right at sunrise or sunset. The sun is super low on the horizon and it casts these incredibly long, exaggerated shadows. That is exactly what's happening along the moon's Terminator line. This low-angle sunlight acts like a massive cosmic spotlight shining horizontally across the surface, throwing every single bump, ridge, and depression into sharp, dramatic relief. Because there's no atmosphere to kind of soften the view, the contrast is absolutely spectacular. Without these shadows, the moon would just look like a flat, glowing disk. They give us the ultimate tool to judge depth and height from literally hundreds of thousands of miles away. Let's look at the proof. Direct your eyes right here. On the left, we're looking right near that Terminator line. Notice how deep and defining those shadows are. Every crater rim pops. Every ridge looks like a jagged sawtooth just cutting into the blackness. You instantly get a sense of how impossibly rugged that terrain is. But now, look over to the right side. That's an area where the sun is way higher overhead. It looks almost completely flat, doesn't it? It's totally washed out. The crazy thing is the physical landscape hasn't actually changed at all, but without the shadows to define the topography, the visual information is completely lost to us. The shadows are literally illuminating the ruggedness. Moving right along to Section 2, Anatomy of Impact Craters, Scars of Bombardment. So now that we know how to use shadows to see the texture, let's investigate those highly textured circular areas we were just looking at. We're talking about the violent history behind these features, the impact craters. When we see a crater, we're looking at the aftermath of a catastrophic event that unfolded in mere seconds. The making of a crater happens in 3 explosive steps. First, boom, a high-speed impact. An asteroid or comet slams into the lunar crust at tens of thousands of miles per hour, delivering just an unfathomable amount of energy. Second, that sheer kinetic energy instantly vaporizes the impactor and blows out the surrounding rock in a massive explosive excavation, carving out a deep, wide bowl. And third, and honestly, I think this is the most fascinating part, the immense downward pressure causes the highly compressed lunar crust to literally snap back up. It's a geological rebound. It behaves almost exactly like a drop of water splashing back up when you toss a pebble into a pond. Except here, it's solid rock. And this brilliantly illustrates that exact rebound effect. Point your attention right to the center of that prominent crater. Do you see that tiny mountain sitting right in the middle of the basin? That is the central peak. That is the literal physical evidence of that third step, the geological rebound, just frozen in stone for billions of years. When that asteroid hit, the lunar bedrock behaved like a fluid for a fraction of a second, bounced up, and then solidified again. So every time you spot a little dot in the middle of a lunar crater, you are reading the signature of unimaginable cosmic violence. Let's look even closer at that explosive excavation step. Here, the deep, pitch-black shadows inside these bowl-shaped depressions give us our crucial visual cue. Because the moon doesn't have an atmosphere to scatter light around, anywhere the sun doesn't directly hit is just absolute inky blackness. By looking at how far that shadow stretches across the crater floor, astronomers can calculate the exact height of the crater rim and the immense depth of the impact. Basically, the deeper the shadow, the more powerful the ancient impact was. It's this incredibly precise visual record of energy transfer. All right, Section 3, Lunar Maria, seas of stone. So far, we've focused heavily on the really violent crater regions. But what about the rest of the moon? Let's shift our focus away from the chaotic impacts and turn to the smoother, darker areas. We are moving from impacts to ancient volcanic fire. Early astronomers looked at these massive dark patches and actually thought they were oceans of water. They named them Maria, which is Latin for seas. Well, they were definitely wrong about the water, but they were actually spot on about the fluid part. The lunar Maria are incredibly dark, smooth, and flat because they were formed by ancient, highly fluid lava flows. Billions of years ago, massive impacts cracked the moon's crust deeply enough to let magma literally bleed out from the interior. This lava was incredibly thin and runny, so it spread out rapidly, pooled into the giant impact basins, and eventually cooled completely flat. It's a lot like how you'd pour hot asphalt to pave a totally flat, dark parking lot over a really bumpy field. We contrast the smooth paving directly with the lunar highlands. Those are the lighter, incredibly rugged, heavily cratered areas that represent the older, original lunar crust. Which brings us to Section 4, the rugged lunar highlands. Now, what's really interesting about this slide is what happens when these completely distinct geological processes actually meet. Look closely at the striking collision of the terrains right here. In the lower left, you've got the smooth, relatively featureless mare. Because it's so flat, there are very few shadows to catch the light. It's literally a tranquil sea of frozen lava. But look at how abruptly it hits that highly rugged, shadow-drenched, cratered edge of the highlands. You can practically see how the ancient lava flowed outward and was just walled in by the mountainous rims of those older craters, freezing like a lake against a jagged shoreline. The interplay of shadow here perfectly highlights the timeline. The rugged highlands were there first, getting battered by space, and the smooth lava came way later, filling in the lower elevations. Let's zoom out to this wider perspective for a second. This is a vast tapestry of the lunar surface, and just look at how much you can read now. You aren't just seeing a mottled gray ball anymore. You can instantly identify the dark, flat Maria and know, hey, that's ancient lava. You can spot the lighter, rugged highlands and know that's the ancient crust. You see the deep shadows near the Terminator line and understand they're revealing the depth of explosive craters or the height of central peaks formed by violent rock rebound. Our new understanding of impacts, lava flows, and just the simple geometry of shadows lets us synthesize all of this. We are truly reading this landscape. So the absolutely crucial takeaway from this explainer is that observation is about way more than just looking. It's about decoding. The light and the darkness, they are our tools. And I want to leave you with this question. The next time you walk outside, look up at the night sky and see the moon rising. What stories of cosmic collisions and ancient fire will you see? You have the tools now. Use them. Keep looking up and keep reading the stars.